So our reciprocal graphs, you can summarize the entire thing in one short idea that all that's happening when you have a 1 over f of x graph is that your y coordinate changes from being y to 1 over y. So all of your y coordinates change to become 1 over what they were. Your x coordinates don't change. Now, this is right at the beginning. This is right at the beginning. The reciprocal function here, we can go right to here. There you go. All that's changing is that your y coordinate changes to 1 over y. But even though that's the simple idea and we could stop the lesson now and say, okay, go do your homework, that's what changes, there's a bunch of interesting things happen when you change the y coordinate to 1 over y. And what also is interesting is when you did things like last semester, you took this parabola like this, and when you did 1 over f of x, I think you called this one the volcano, right? It had a couple asymptotes, and then the graph went like this and like this. And so even though it's a simple idea that all that's happening is your y value is changing to 1 over y, the graph that you get looks totally different than the graph that you started with. The new graph, the volcano graph, doesn't look like the parabola at all. But all we did was change one simple thing, the y coordinate, to 1 over y. Well, we're going to figure out, why does a graph change so much? What are some of these interesting things? Well, if we were going to graph something, the first thing you're going to do is graph your original function. So if you had the parabola, here's the original function that you would graph. Once you've graphed that original function, wherever you have x-intercepts, you're going to draw asymptotes. Because what happens at this x-intercept? What's your y value? Your y value is 0. What happens when I change my y value to 1 over y? I have 1 divided by 0. So wherever we have an x-intercept, we have a non-permissible value. And how do we show the non-permissible value? We show that with an asymptote. So we're going to have vertical asymptotes wherever your original function has an x-intercept. Sometimes you might have a bunch of x-intercepts. When we do the graphs of sine and cos, we're going to have an infinite number of x-intercepts. So you would have an infinite amount of asymptotes. Once you're done drawing your vertical asymptote, you're going to draw your horizontal asymptote. Now, on our graph here, we ended up with a horizontal asymptote at y equals 0. That happens because as your y values here, they get bigger and bigger and bigger and bigger. Somewhere along here, the y value is going to be 100. So on this graph, your y value at that point would be 1 over 100. But if it keeps getting bigger and bigger and bigger, you keep getting a fraction 1 over a bigger and bigger and bigger number. And if we think about what happens as we look at a fraction that's 1 over a bigger and bigger number, it gets closer and closer to 0. It never equals 0, it just approaches 0, and that's why we have an asymptote at y equals 0. Again, an asymptote on a graph is that what your graph is getting close to but never equals. And so as this fraction, the number on the bottom, gets larger and larger, that fraction is going to get closer and closer to 0, even though it never equals 0. So if your graph either goes to positive infinity or negative infinity, if it either goes up forever or down forever, you will have an asymptote at y equals 0. Once you've drawn both of your asymptotes, here it says plot all the points that are equal to 1 and negative 1 you could take this step. Sometimes the points where it's equal to 1 and -1 aren't easy, so I just say plot some points. Maybe there's some points that you know. Maybe 1 and -1 are part of those. Maybe they're not. So let's say if this graph had 5, 1 and 6, 4 as points, if those are points you know on your original parabola, you can plot where those points are going to go. Again, following the simple rule that all that's changing is your y value is changing to be 1 over what it was. So when I look at 6, 4, I'm now going to have 6, 1 over 4. And when I look at 5, 1, I'm now going to have 5, 1 over 1, but 1 over 1 is still 1. So that's why in this step right here, we call those ones invariant points. Because where you have values of 1 and -1, when you do 1 over that, it doesn't change. So step 4 and step 5, basically you can combine into one step and just say, plot some points. Plot as many points as you know, plot important points. So number 5 is saying if you know maximums and minimums, those are going to be important points to plot. Because they're going to be easy to figure out and they're going to be key things. And also what happens is wherever you had a maximum, it becomes a minimum. And wherever you have a minimum, it becomes a maximum. So we'll see that in some of our examples. And the last thing, once you've plotted some points, you're going to draw your graph, and you're going to draw your graph going towards your asymptotes. So I've said draw it showing some asymptotic behavior. Because what's happening is your graph is going to approach those asymptotes. So what we're going to do is we're just going to look through these examples on that second page that I gave you to get a sense of what's going on. We'll start with example 1. We're going to graph 1 over x squared minus 4. So we're going to start and look at okay, there we go. So the first thing we're going to do is we're going to graph the bottom. Here we've got the graph of x squared minus 4. That's a parabola that's been moved down 4, right? Then I've got each of the steps separate, but chances are what would happen here is right beside it you would have your final graph that you were going to graph. Here you've got x squared minus 4. Do we have any x-intercepts? Yes, we have an x-intercept at minus 2, and we have an x-intercept at positive 2. So you take out your red pen and draw an asymptote at minus 2 and at 2. So I showed that all by itself as a step, but in reality you would do this on one graph. You wouldn't show each step separate like this. But for your notes, each step is separate. So you would draw those asymptotes first, then you would look at your graph and say, does my graph go up forever to positive infinity or down forever to negative infinity? Yes, my original graph keeps going up, right? And so you would have an asymptote at y equals 0. Now steps 4 and 5 is just plot some points. What are some points that you know on x squared minus 4? Well, you know 0, negative 4, right? So where's that point going to go? 0, 1 over negative 4. What are some other points that you know on your original parabola? If you can't think of any, just put some in. Like for example, what happens when x is 1? What point do I have? I'd have 1, negative 3, right? So where's that point going to be? 1, comma 1 over negative 3. What's another point that you know? What happens when you plug in 3? Do you see that you'd have 3, comma 5? And same thing over here, you'd have negative 3, comma 5. So where's that point going to be? 3, comma 1 over 5 and negative 3, comma 1 over 5. Now you could keep going and draw more and more and more points if you wanted, but once you have a point in each of the 3 sections, because your vertical asymptotes separate this into 1, 2, 3 sections. Once you've got a point in each of your 3 sections, you can go to the last step, which is draw the asymptotic behavior. So I know that it goes through negative 3, comma 1 over 5. Because I have asymptotes there and there, it has to do that in that section. And I have 2 points here in the middle section. This 0, 1 over negative 4 was a minimum here, so it's going to be a maximum in this section. And because I have asymptotes, I know it has to go down, because if it went up, it would go through those asymptotes. Also, because this was a minimum, I know that that's a maximum in that section, and so I know it can't go higher than that. And finally, the last section would go through there. And this one, what do we call this one? The sad face, yeah. Okay, let's go to example 2. Hopefully it's happier. So now we're going to graph 1 over x squared plus 1. There's the graph of x squared plus 1. Our transformations would take our x squared graph and move it up 1. So right beside, because if you were doing this without showing all the work, this is how you'd start. First of all, it has no x-intercepts, so there's no vertical asymptotes. But it does go up forever, so you do have an asymptote at y equals 0. So we draw our horizontal asymptote and label it at y equals 0. What are some points that we know? Well, this one's going to be important because it's a minimum at 0, comma 1. So we're going to have 1 over 1, which stays 0, comma 1. What's another point that you know on your graph? 1, comma 2. What's going to happen to 1, comma 2? 1, comma 1 over 2. Now, technically, we have enough points already to graph this, because we took our minimum point, so we know that that's going to be our maximum point. We only have one section for this graph because there are no other vertical asymptotes, and it's only the vertical asymptotes that separate it into different sections. So we can draw the asymptotic behavior because this is the maximum now. It's going to have to go down towards the asymptote and down towards the asymptote again. What did we call this one? Speed bump. We should have done 1 over negative x squared minus 1, so we could have done potholes because it's Winnipeg, but we have a speed bump. Now, both of these examples were ones that you did last year in grade 11, because both of them took parabolas and did 1 over parabolas. Okay? But we can now do any of our functions that we've done so far and do 1 over them. So here we have a square root graph, the square root of x plus 4, which is a square root graph moved 4 to the left. And right beside this, we're going to go through our steps for a reciprocal graph. Do we have any x-intercepts? Yes. We have an x-intercept at negative 4. Does our graph go up to infinity? Does it keep getting bigger and bigger and bigger? Does the square root graph eventually stop, or does it just keep getting bigger? Keeps getting bigger. It slows down, but it still keeps getting bigger. If you think there's a value you can't get bigger than that, square it and add 5 to it, and you'll be bigger than that when you square root it. So it will have an asymptote at y equals 0 as well. So now that you've got your asymptotes, now let's take some points. What are some points that we know on the square root graph? Well, we have negative 3, 1. What's going to point? It's going to stay negative 3, 1. What's going to happen to 0, 2? The y values change to 1 over y. So it becomes 0, 1 over 2. This asymptote, split it into 2 sections. How do we get a point in section 1? You don't, because there's no domain in section 1. So we don't even have to worry about anything in section 1. We've already got some points in section 2, so we can draw our final graph approaching the asymptotes. And sometimes you're going to be given some weird graph and asked to do the reciprocal graph of it. So here we've got a bunch of straight lines joined together, and the graph is already given. Technically, these are supposed to be the easiest ones because step 1 is done for you. Because then on the first 3 examples, step 1 was always graph what was on the bottom. Right? And then you could graph the reciprocal. But this one, the graph is already given to you. So we just have to go through, do I have any x-intercepts? Yes, I have an x-intercept at -1. So that'll be an asymptote. I have another x-intercept at 2. And another x-intercept at 5. Does our graph go up forever? Is there an arrowhead on the end of the graph? Well, there's no arrowhead here, so it stops there. But over here, it goes up forever. So we do have an asymptote at y equals 0. If we look at some of our points, -5, -1. That'll become 1 over 1, or sorry, 1 over -1, which will stay the same. Can you see that -2? -1 will also stay the same. In fact, this whole section will stay a straight line right there, because all of those y values are 1. We have 0, 1. That point's not going to change. We have 4, -1. That point's not going to change. And we have 6, 1. That point's not going to change. Now, technically, we have points in each of our sections. We can draw things to show our asymptotic behavior. We would be able to do that. But if you wanted to, you could do some other points. For example, here, if I have 4, -1 here, it looks like I have 3, -1/2. What happens when you do 1 over 1/2? Well, it's a reciprocal. So you can even just take the fraction, -1/2, and flip it. What do you get? -2 over 1. Ooh. So you'd get the point 3, -2. So if you wanted to take some of those points, you could flip them. However, you would have enough information because check out 0, 1. Can you see in that area it's a local maximum? So that means in this section it has to be a local minimum. This part goes up towards the asymptotes. At 4, -1, it's a local minimum. So that means in this section, 4, -1 is a local maximum. Here, what's going to happen? Well, if we did take this point and say, what's that? That's at a half. And if I do the reciprocal of half, where's that going to be? It's going to go down to 2. Oh, I have to go down here. And you might have been able to see that to say, oh, this straight line is a bunch of minimums. So here it's got, that straight line's got to be in that area a bunch of maximums. Okay? You're going to be tempted to make this arrow keep going. But there's no graph over here, so this has to go away and you can't have it there either. And finally, in this last section, this will go up towards the asymptote and it will continue forever down towards our asymptote there. So there's a worksheet there to practice reciprocal graphs.